So in this video, we're going to cover some proofs. A very important part of this course is the ability to give proofs or to come up with proofs for various geometric or discrete geometric problems. I know that for a lot of you, coming up with proofs or proving something could be something new. You might not have much experience with it. So here in this course, we'll have to practice that, because some of the projects are actually theoretical projects where you have to prove something, prove a claim or prove a property, and etc. So here we're going to practice that. So the first thing we want to practice is we want to prove that it's always possible to triangulate a simple polygon. And we want to prove it using induction. Right? So before bringing up the induction, let's go back. So when you have a picture like this, what does it mean that it's always possible to triangulate this polygon? What it means is that you can draw these line segments that go through the interior of the polygon such that the final result is just a collection of triangles. So for example, if I stop here, then that's not correct because I have this region that is not a triangle, but then if I connect like this, then I'm done. Every region in this picture is a triangle. This seems obvious. Why would it not be possible? Well, it won't be possible because sometimes you cannot draw some edges. Like for example, you cannot connect this vertex to this vertex. If you want to make this connection, that's not allowed. It goes through the outside, it intersects the polygon, and etc. Right? So that's not allowed. And on top of that, like if you draw this edge, then that stops you from drawing this other edge. That's also not allowed. You cannot have a triangulation where you have an intersection point between the edges that you draw. So you have to be very careful. So one idea when it comes to triangulation is to try induction. And the idea is actually very simple. If you draw any edge that goes through interior of a polygon, then you can essentially think of this polygon as being decomposed into two polygons. You have a polygon over here, actually call it quadrilateral here, and then you have a smaller polygon over here. And if I want to use induction, then I know that this polygon on this side can be triangulated, and this polygon on the other side can also be triangulated by induction. So that means if I want to use induction, then the problem just boils down to being able to draw one edge. Okay, and that seems like a very easy and obvious thing, that of course you can always draw some edge inside a polygon. Why would it be impossible? Well, but that's not a proof. To be able to come up with a mathematical proof, we have to be able to rigorously prove that you can always draw an edge or make a connection between two vertices of a polygon such that the edge goes entirely through and doesn't cross a boundary. Of course, if your polygon is just a triangle, you have nothing to prove, it's already a triangle. If it's a quadrilateral, it has four sides, then you can say that, okay, we have two cases. We have like the convex case of a quadrilateral and let's say concave, which looks like this, for example. Now you can see why this gets a little bit challenging, right? Because if your picture looks like this, then there is exactly one edge that you can draw. You can only connect these two. If you try to connect, well, this other thing, that's not allowed. So it could be a bit tricky to find the two edges that you can always connect, or two vertices that you can always connect. All right, so in other words, what I'm trying to say is that this is not as obvious as it looks like. Okay, so how can we solve this? The idea here is to come up with a strategy and then try to improve it or fix any potential problems that you can have with that strategy. Let me explain what I mean, or let's look at some of the details. Okay, the first thing we see is to make an observation here that when I look at the vertices of a polygon, some of them have angle higher than or smaller than 180, but some of them have really large angles. And the vertices that have large angles are kind of a bit tricky to deal with, whereas these vertices look nicer. So if I could always find a vertex like this and connect its neighbors together, then I'm done. Right? Of course, if this angle is less than 180, then I could always connect the neighbors and it will go kind of through inside, through the interior, at least at the beginning. Whereas if I have a vertex that has angle bigger than 180, then if I want to connect the two neighbors together, then it will go outside for sure. So therefore, to find two things that I can connect, maybe I can start with these kind of vertices and not these kind of vertices. I think I'm gonna go to through the proof in the next video so that you can find it easily. So I'll just stop this video right now here.